Hello everybody. In this video, we're going to learn about tangent planes to multivariable functions. Now, in the previous video, we learned how to write down the equation of tangent lines to a multivariable function. That might have been a little bit strange because if you're talking about a surface, there's lots of tangent lines to a surface at any one point. A tangent plane to a surface is more closely analogous to a tangent line on a curve. In particular, if we have regular old calculus, some kind of a curve, there's really only one tangent line to a curve at a given point. Now, if we look at the case of multivariable mathematics, right here, this blue hill shape, I'm thinking of that as a graph of my multivariable function. There's exactly one tangent plane to this surface at a given point. And a tangent plane has the same properties as a tangent line to a curve, in that it only intersects the surface at a single point, and it has the same slope, or in this case, slopes, in each direction at that point as the surface does. And so if we were to calculate the slope of the tangent plane in the x direction or the y direction, they would agree with the slope of the surface in the x direction and the y direction at that point. So our goal is to find the equations of these planes. Just as a quick review, the equation of a plane has the form a times x plus b times y plus c times z equals d. The vector n, with components a, b, c, the coefficients of x, y, and z, that's the normal vector to a plane. It's a vector which is perpendicular to a plane. And if we wanted to calculate the normal vector, in other words, if we wanted to calculate the equation of a plane, it requires 3 points in the plane. We'll call them P, Q, and R. And to calculate this normal vector, first we need 2 vectors in the plane. So we could calculate vector V as point Q minus point P. Then vector W we could calculate as point R minus point P. And then the normal vector should be perpendicular to both of these vectors in the plane. So the normal vector n can be calculated as the cross product of v and w. Right, that gives us the values of a, b, and c. That gives us everything we need for the left-hand side of the equation of a plane. To calculate the value of d, we could just calculate the normal vector and the dot product with one of these points on the plane. And that gives us everything we need to write down the equation of a plane. In this case, we'd like to write down an equation of a plane, but we do not have 3 points on the plane. Right? In this case, we're usually given a surface, z, is a function of x and y, and we're given a single point on that plane, not 3 points. So in order to get these 2 vectors, v and w, that we need to calculate the normal vector, we'll use the slope vectors in place of v and w. And that's an important choice because remember, we want the plane to have the same slopes as the surface does at this point. Now in the last video, we laid a lot of the groundwork for this video without even realizing it. The slope vectors that we need, we know how to calculate. The slope vector in the x direction is 1, 0, and the partial derivative of z with respect to x. The slope vector in the y direction is the vector 0, 1, and the partial derivative of z with respect to y. Once we have these 2 vectors, we can calculate our normal vector to get a, b, and c, and we can calculate a dot product with a point P to get D. So let's do an example. Let's say we want to find the tangent plane to this equation, z equals x squared times y cubed, at the point xy equals 1, 2. Well, as always, just like we needed for tangent lines, for tangent planes, we need a point on that plane. To get the point P, with coordinates x, y, and z, we're given the values of x and y, and then we need to calculate the value of z from the equation of the surface by plugging in the values of x and y. So we know that a point on this plane is 1, 2, 8. And, not sure if you remember, but we're actually reusing the same function as we did in the previous video, and so we've already calculated the partial derivatives of this function. The partial derivative of z with respect to x is 2 times x times y cubed. The partial derivative of z with respect to y is 3 times x squared times y squared. And then, if we evaluate these partial derivatives at this point, which is also the same point we used before, we'll find that dz dx equals 16 and dz dy equals 12. And that gives us our slope vectors, 1, 0, 16 and 0, 1, 12. Next, we need to calculate the cross product of these two vectors. And so you can always feel free to go back and review the earlier video if it helps. But the basic algorithm is this. We'll create a 3 by 3 matrix. The first row will be the standard basis vectors I, j, k. The second row is components of v, and the third row are the components of w. And we calculate this 3 by 3 determinant as, well, 2 by 2 determinants. And so we have our I and our j and our k. Remember, we need alternating signs here, so positive, negative, positive. Never forget that negative sign in front of the j component. And then, to figure out the coefficients of the 2 by 2 matrix in front of each of these vectors, right, for I, ignore the values in the same column as I, and these remaining values form that matrix. For the matrix in front of j, ignore the values in the column of j, and those remaining values form that matrix. And then for k, ignore the values in the column of k, and the remaining values form the matrix coefficient of k. Then for each of these matrices, we calculate a 2 by 2 determinant. Right, top left times bottom right minus bottom left times top right. Right, so these three coefficients are negative 16, negative 12, and positive 1. Then, because these are the standard basis vectors, you can really just use these coefficients and create a single vector. Right? I is really the vector 1, 0, 0, j is really the vector 0, 1, 0, and k is really the vector 0, 0, 1. After you do your vector operations, you'll be left with a vector negative 16, negative 12, 1. That's your normal vector n, and that gives us the coefficients of x and y and z. To calculate the value of d, the constant on the right-hand side of the equation of our plane, we can calculate this by computing the dot product of the normal vector n with a point on our plane, which we earlier found to be 1, 2, 8. So when we calculate that dot product, we have negative 16 times 1 plus negative 12 times 2 plus 1 times 8. And when you add that all up, you end up with negative 32. Therefore, the equation of the tangent plane to this surface is negative 16x minus 12y plus z is equal to negative 32. Now, to save our future selves some work, we can actually pretty easily derive a general formula for the normal vector n for the tangent plane to a surface. And here's why. The two vectors we use in this calculation are slope vectors. And from our previous work, we know that the slope vectors will be the vector 1, 0, dz dx, and the vector 0, 1, dz dy. Now let's calculate the general cross product, right? The cross product using these two vectors, right? With the as of yet uncalculated partial derivatives. Right? Just as before, we're going to set up a series of 2 by 2 matrix determinants, the same process as before, and when we calculate the coefficients of I, j, and k, we find we have the numbers negative dz dx, negative dz dy, and 1. Right? And when we do an actual problem, an actual exercise, we will calculate the partial derivatives and substitute in the values at the point xy, so these will become numbers. Now, again, looking out for our future selves and trying to make this calculation a little bit easier, a few less negative signs are always appreciated. Any multiple of a perpendicular vector is still a perpendicular vector. Right? If we were to do scalar multiplication on this vector, it changes the length, but not the direction. So we could theoretically multiply this vector by anything we want, and it's still perpendicular. So let's consider multiplying it by -1. In that case, we get a positive, and negative sign. And so, in general, we'll use that when we're using this formula. So we'll use the normal vector, partial derivative of z with respect to x, partial derivative of z with respect to y, and -1. Now, as an example of how much faster the calculation goes in this case, let's use this formula for the normal vector in the process of calculating the tangent plane to the multivariable function z equals 2xy plus y cubed. Let's calculate the tangent plane at the point xy equals 3, 2. Well, first, let's calculate a point on the plane. So the point P equal to xyz, x is given as 3, and y is given as 2. To calculate z, plug in 3 and 2 for x and y, and you'll find that z equals 20. Next, we need to calculate the partial derivatives of this expression. The partial derivative of z with respect to x, we treat x as a variable and y as a constant. So we have 2x times a constant. In other words, 2 times a constant times x. Well, the derivative is just the constant coefficient of x, in this case 2y. The derivative of y cubed in this case, right, since x is a variable, y is a constant, y cubed is a constant, the derivative of a constant is 0. So there's no other term that makes an appearance. To calculate the partial derivative of z with respect to y, well, we treat y as a variable and x as a constant. Here we have the derivative of a constant times y. So that derivative is just the constant coefficient of y. The derivative of y cubed with respect to y is 3y squared. So that's our partial derivative dz dy. So our normal vector is dz dx, dz dy, -1. So we need to evaluate these partial derivatives at the point xy equals 3, 2. So plug these values in, right? Plug 2 in for y, you get 4 for this first part. Plug 3 in for x and 2 in for y, we'll get 18 and -1. That's going to give us the coefficients in the equation of the tangent plane. 4x plus 18y minus 1z is equal to d, where d is calculated as the normal vector n times, or dot product with the point P. So that's 4, 18, -1, dot with 3, 2, 20. So we have 4 times 3 plus 18 times 2 plus -1 times 20, which works out to be 28. That's the constant on the right-hand side of the equation, and that finishes our calculation of the tangent plane to this surface at this point. As always, you learn math by doing math. So here's an exercise I'd like you to practice on. I'd like you to find the equation of the tangent plane to this surface. Z equals x cubed plus 7xy plus y squared at the point xy is equal to 1, 2. All right, good luck with that, and thanks for watching.